ト次元先。
So I won't say anything that's outside the scope of what we demonstrated there.
ホイールのヘッドじゃない。
Follow this shorthand because it's interesting. Alright, so for any simplex, such as the 100 simplex, there is a quantity of n minus m simplices within it, which is exactly the quantity that are called prime simplexes. So simplex integer is just a number. It's a more powerful number than a digital number because the essence of a number, as said by one mathematician, is the set theoretic combinatorics within the number. Now, of course, an arbitrary symbol, such as how we draw 5, does not have any self-referential symbolism in it, and it certainly doesn't in any way, as a symbol, describe the set theoretic combinatorics of the number, the integer 5. However, when you look at simplex integers as symbols representing integers, it not only gives you the numerical count of the integer itself, just as your arbitrary integer does in digital integers, but it also gives you the full set theoretic combinatorics in a very non-arbitrary way in a principle called self-referential symbolism. So they're powerful, these simplex integers. And I want to describe a very important difference between digital integers, which are arbitrary man-made symbols as integers, versus non-arbitrary simplex integers. It's can be understood with a simple idea. So when we're talking about the Riemann hypothesis and the distribution of primes, we're really trying to ties into the ability to predict the quantity of prime numbers that exist with some arbitrarily chosen number. And so the method of when we use digital integers, in order to get them to converge, we have to invert them. Okay, so when we do this, we continue the series to convergence, we see at the end this beautiful relationship to a number that you normally associate with geometry, which is pi. So we get this beautiful convergence with pi. With simplex integers, we don't need to invert them. Okay, so I'm going to write pi there because I want you to pay attention to the fact that it's a transcendental irrational, right? Which means it doesn't have an algebraic expression. And when we use simplex integers, and we study something such as the circumradii, the series. First of all, the circumradii series going from the 1 simplex to the infinite simplex ranges the span of 1/2 to square root of 1 over square root 2. So that's the span. So the circumradii of every single simplex integer fits within this bound. So if we only pay attention to the prime series, and it converges rapidly. Okay? The distribution of primes thins out over as you go deeper down the number line. It becomes more sparse. And so we'll call that the numerical density. So the numerical density becomes more sparse with digital integers. The spatial density on the one-dimensional line also becomes more sparse over space. So spatially and numerically, you have sparseness as you go further down the number line. It's very interesting with simplex integers because the numerical density, of course, trivially is identical to in other words, when you look at the density, when you look at the quantity of 23 prime simplexes within the 100 simplex, it's a trivial thing. There's 23. You know exactly how they're spaced out. So what you do is you take the circumradii of the first one of the first prime, which is 1, and that's 1/2. So you can draw that as a circle, and then you take the circumradius of the next prime simplex, and so on. And what you get is a set of concentric rings. And you can draw a line for the set of concentric rings to get a one-dimensional distribution. And numerically, that distribution drops in density identically to the distribution of prime density numerically. But unlike the digital integers, which also drop in spatial density, the distribution in prime density of the simplex circumradii on the one-dimensional line actually increases in density. It's very, very interesting because you go further and further down, and because of the extreme rapidity of convergence of this value to this value, which is a distance value, it far surpasses the increase or the rapidity of the thinning out of the digital. So you can get a ratio that you can study here for prime number theory. So you have this ratio, which is with simplex integers, which is your spatial ratio, your spatial drop in density. So you pick a span and you say, I want to calculate what is the drop in density of prime simplex radii over space in 1D, and you get a number. Okay, and then you get another number when you analyze what the density numerically is and how that drops. So this density increases, and this density, numerical density, decreases. And for some span of primes, there's a calculable ratio that can be used. So you can go to different equal spans along the number line, and you can check, is the ratio of these two, this increase in density and decrease in density, the same no matter where I go? Does it change depending on what span I take? And what's the rate of that change? How can I analyze how it changes from span to span in terms of the ratios of these numbers? The point that I'm making is that there's more rich and non-arbitrary information in simplex integer number theory than there is in digital number theory. So the next thing that I'll add to this is two problems. The first is that problem that I just defined. It's been some years, but I don't want to be too distracted from prime number theory. But I want to tell you about quasi-crystals and how it relates, and this is the second problem. It's a harder problem. That problem that I said is a one-day problem for someone like Ray or Todd or somebody who's played with this. And it's a problem that's never been written down in the literature, I'm sure of that, from the research we did when I made that paper. The other thing is quasi-crystals. So Freeman Dyson says, he argues and explains from a mathematician's point of view why the distribution of primes and the distribution of non-trivial zero is a quasi-crystal. So the thing about quasi-crystals is one can say that a proper hyperlattices and projections that generate the same aperiodic point set that you get on the distribution for the non-trivial zeros or prime numbers themselves. But what you can do is you can understand that each prime simplex maps to an A lattice, right? So an A series lattice. So for example, the simplex integer for the number 4 is the free simplex because it's the equidistant array of 4 points in free space that describes through its lower dimensional simplices the exact set theoretic combinatorics for the number 4 or the number 1 million or any number. And so then you can extend that and you can say, well, can I study prime number theory through these geometric numbers by the A-n lattice series? And of course you can, such that within the A100 lattice, you have within it 23 prime A lattices. And the distribution of those prime A lattices within the A100 lattice is exactly the distribution of primes on the number line. And so where you want to try to do analysis is by irrational projection. So you can project that A100 lattice down to 1D and find a rational value. And you get a point set, which is quasi-crystalline in 1 dimensions. Now the trick is, how do you isolate out in that projection the prime A lattices so that you can study the distribution of prime A lattices within this point set? It's very tricky and confusing. So I described one method of doing prime number theory by studying the ratio of the drop in density numerically over the circle radii of the simplex series. And as a ratio of the spatial density, which increases. So it's the prime number, the prime simplex. So let's say this is a prime radius, and this is not a prime radius, and this is not a prime radius, and so on. You have a distribution where you say I'm only studying in this series of circle radii of these simplexes the distance between radius, their numbers that are lengths. So then you have this aperiodic distribution of points that represents the circle radii of prime simplices. That's one way. That's the one problem that I suggest is about a day's work of somebody who understands this. It's not a hard problem to work, program a solution for, and mathematically kind of understand. But a really hard problem is a more sophisticated way using quasi-crystal mathematics, and that would be to understand a simplex by extension into the A lattice. So the simplest n-dimensional element of any A series lattice, A2, A3, and so on, is the n simplex corresponding to the A series lattice. And so similar to the statement that the distribution of 23 prime simplexes within the 100 simplex is exactly the distribution numerically of the digital integer primes within the span of 100. I want to come back to this for a second, because the way that we study the Riemann hypothesis for 100 years in prime number theory is to use the prime number theorem, and it's a way to predict, in every case, an incorrect prediction of the quantity of prime numbers within a map. It's never right in any case, but the larger your span of numbers that you put the primes in, the more accurate the prime counting or prime number theorem counting method is. So that if you go all the way to infinity, it can be accurate, but any finite bound is always inaccurate. And it's the inaccurate. So for example, when you're doing 100, the prime number theorem, which is based on the other most popular transcendental number with no algebraic expression E, that gives you a significantly wrong number. So they're 23, it gives you 18, very wrong, right? And it's the wrongness, it's a really complex mathematical process, it's the wrongness of the prime number theorem prediction that maps to the non-trivial zeta zero distribution. That alone is a very sophisticated proof that I don't even understand, but that Ray assures me is true, and that we put in the paper. And it's in our paper, but I couldn't reproduce the math to show that mapping. But let's assume it's true. So therefore, the deepness of proving the Riemann hypothesis is understanding why this prime counting function based on a transcendental number is always wrong in every case, and how that wrongness maps back to the distribution of the non-trivial zeros. The non-trivial zero distribution is very much the same problem in a more sophisticated form as the problem of understanding what in the world causes and allows one to predict the distribution of prime numbers in any bound along the number line. So as you can see, when you analyze this question, why would there be 23 prime simplexes within the 100 simplex? Okay, you can clearly see the answer to that question, the way I posed it, is a purely geometric question, where geometry makes contact with set theory, group theory, number theory, but it's a deeply geometric problem. And I remember with those simplices, and I remember that it was a relationship between the binomial numbers. Remember, right? I remember vaguely. So I don't want to go over my time, but too much more. But Marcelo asked a question. I'm still in the process of answering it, and then Mia wants to ask a question. I'll let you go before me if you don't mind just going.
Okay, so there's a question.
How we think about codes. Well, what we're doing is we're trying to... Yeah, I mean, how it might correlate, I'm not 100% sure, but there's a lot of papers in addition to the one that Carlo and Ray and myself did on showing how there's this mysterious and very interesting correlation between quantum mechanics and prime number distribution and the Riemann hypothesis. It's very deep. Nobody has the convincing killer answer, because perhaps the convincing killer answer requires some deeper understanding of why it's been 150 years and we still are seemingly on the wrong track with proving the Riemann hypothesis. So back to it's how it relates to the way I think. I think everything is symbolism, and I don't like arbitrary symbols, because anybody can make it up. I like self-referential symbols that are not arbitrary mathematical objects such as n simplices, and those things can have non-arbitrary intrinsic meaning in mathematics. And so of course our whole program here in quantum research is about trying to use self-referential symbolism, of which form is quasi-crystals, which are languages or codes made of self-referential symbols, syntactic freedom, and so on. So somehow this eventually, when we figure out our program, we're somehow maybe going to have deeper insight starting to get glimpses of how nature is literally made of mathematics, and geometry is mathematics. So we live in a geometric reality. So it's this deep idea where you think about all of mathematics as an upside-down pyramid, starting with your choice of set theory or number theory, right? But in my opinion, counting numbers come first, because you can't count sets without counting numbers. It's hard to study set theory without numbers, but we can say set theory is more fundamental. Okay, but just so you guys know, I have one more thing to say, which is answering Marcelo's question, and then I'm done. We can first.
Yes, it will be short. I will just to explain to everybody here what is our geometric criteria of primality. Is that if you have a simplex of any dimension, and you are counting the subsimplex of any dimension, for example, for a tetrahedron, you are counting the points, the edges, the faces, and you are coloring them, for example, for a tetrahedron in 4 colors, you should have the same number of points and elements of each dimension of each color. And for the tetrahedron, it doesn't work, so this is proving that this is not prime number. For the pentagonal, it works. Everything can be colored with 5 colors. So if you can see in high dimension and virtually make this coloring operation, you can, in one glimpse of view, see that this number is prime or not.
Okay. So on all of this,
just one comment on this.
Okay.
The connection is 1 primes and 1 octave. So if you have a problem more, things will be more fluid. You have a higher dimensional hyperspace, but you always can decompose this. And sometimes you can translate this to like a higher dimensional sequence. You can decompose in the P, which is our lower dimensional sequence. Yeah, sequence.
Okay, so say the last two things, which I want to answer Marcelo's question, which was my problem number 2 anyway, and then I want to point out why I was emphasizing these two transcendental numbers. So all prime number theory is deeply involving these two numbers. This is what the zeta series converges to, with another couple symbols here, and then the basis of prime number theory, whether you use one of the more modern derivatives of the prime counting function or the original one, it's based deeply on another transcendental E, and so whatever's going on, when you use this E, you get a mistake, an incorrect prediction, and then you map that prediction deeply to this Riemann hypothesis. So when you're dealing with simplex integer number theory, to do the same types of problems, but you convert it to geometry, you use algebraic irrationals. And that's interesting. It may not be important, but it seems to be an interesting difference to at least keep note of in your mind. So now the last thing is just defining the second problem. So the second problem is to study the spectrum of prime distribution within a projection. So this was a kind of thing that's artificial. Well, this is a manipulation of if I were to take 100 simplex, I'd have to go around it, find all the n minus m simplices measured that are embedded within it, and then take their circle radii and then plot all their circle radii out where they share the centroid of these circles, and then draw my line through it so I can derive my one-dimensional spectrum of prime simplex distributions. And so anyway, so one question is, when I do that, and I do it Fourier transform, do I get discrete Bragg peaks indicating a quasi-crystal mathematically, or do I not get discrete Bragg peaks? And so now, repeating what I said before, let's move beyond n simplices and take the extension of the n simplex series and study the problem the same way. So when we think of the simplex integer 3, it is the 2 simplex. And when we extend this out to its lattice form, we build out the A2 lattice. And so we can go to the 100 simplex again, which has 23 prime simplices within it, and we can extend that out to the A100 lattice, right? And within the A100 lattice, there are 23 prime A lattices embedded within it. We take some irrational angle to project the A100 lattice to 1D. And the thing about irrational projections is they allow you to preserve a great deal of information about the higher dimensional object, whereas rational projections will cause you to lose a tremendous amount of information. So somehow, the conjecture that needs to be explored is how we want to mathematically analyze this one-dimensional spectrum from some projection of the A100 lattice to pay attention to the density distribution over space and number and their ratio of the A prime lattices that are represented within that one-dimensional irrational projection. But you don't have to do it in one dimension, you can do it to any lower dimension, like 2D. But it's a hard problem. So Ray and I thought about it for a while, and then we had already spent a long time on the paper and the research behind it and all of that, and decided to put the problem on hold. There is one more thing that I'll say relating simplices to prime numbers. So the prime numbers, when you study them via simplices, have come in 2 mirror sets, which are equal. So if you go to infinity, half the primes are on one set in this base 6 structure, and half are on the other. But we can understand the base 6 by first principles by taking we take the simplex series that gives the set theoretic combinatorics for each simplex, and that is Pascal's triangle. So when you look at Pascal's triangle, then what you're reading in that is the set theoretic combinatorics of any n simplex that relates to the line on that part of Pascal's triangle. It's the binomial coefficients, and then so when you then study that, it's explained in the paper. When you study that, then you realize, oh, okay, there's really a fundamental non-arbitrary bifurcation of the prime numbers when you study it via simplex series, the set theoretic combinatorics of simplex number theory, which is expressed in Pascal's triangle, and then you get these 2 lines. Now the lines are they're increasing in wavelength. Okay, if you just were to draw them out on the digital number line, and then you understand that half the primes are on one of these wavelengths that increases in wavelength, and they're offset. So then, again, what is most interesting to me is the extra information or ratios that you get, because in the case of what I suspect that maybe man-made integers in some weird abstract way are not natural way they are and the way they're not. Again, I'm not talking about the symbols, like how we draw 5. I'm talking about how you lose information, because here, when I use simplex integers, I actually have a different delta, a piece of information between this sequential pair of integers and the next sequential pair of integers. It's a different distance, but when you look at the distance between 1 and 2, and then the distance between 2 and 3, it's the same distance. So it's that homogenization, that loss of information with digital integers that may be the root of this 150-year-old problem, which is really a 2,000-year-old problem if you go back to the mystery of how to predict or understand the pattern of prime distribution. So I believe this is an easy problem, is a one-day type of simple problem, and this other thing I'm talking about is a very hard problem, because it requires, I have this all, I can write this down and tell somebody exactly what to calculate. With this, I can't, because I can't tell you what the irrational angle should be, I can't tell you if it matters what the irrational angle is, and I can't even tell you how, in the 1D spectrum, how you would eliminate the non-primes so that you can study the spectrum. I don't know, but I believe there may be answers to it, but this way is for sure straightforward. This method here gives you real distance numbers in this, and then the ratio. So it's a very juicy problem. It's not our physics yet, because we don't know what our physics is yet, but I have an intuition that there's a convergence in the future between number theory, prime number theory, and the Riemann hypothesis in particular, and fundamental physics. So if we were so bold as to speculate that our pathway is on the vector toward discovering nature's symbolic genetic code, then every mathematics number is counting numbers. So maybe there. So if I can find some person like Carlos, anybody that came into it, I'm gonna give you the hard copy. Julia's giving you a hard copy now. If you study this paper, it's not like my essays. It's not a talking about consciousness or essay type of stuff. There's some essay stuff in there that I can't resist, but in there that's progress explaining this in greater detail is very, very interesting. And you're so smart for both geometry and number.
Remember the connection between pi and the zeta function. Only because when S is even, when S is even, the zeta function gives you a number of pi because of the Bernoulli numbers. So the Bernoulli numbers, the whole important key in that.
So I actually think that somehow, in a weird way, pi and e, these two transcendentals, are problematic. I'm joking, but I don't trust a number that doesn't have an algebraic expression. I'm joking, but I'm saying that between two irrationals, if one has algebraic expression and the other doesn't, I trust that algebraic expression. That's less controversial.
I tell you, if I give you the simplex, the n, the 1000 simplex, can you tell me immediately how many primes it has?
We have an algorithm that will tell you without any effort that it's prime.
It's by seeing the number of the different dimensions, given whether or not the number is given as a binomial function. If you can see that the dimension is
that prime 1000 simplex has n primes in it, or him giving you the digital number of 1000. In other words, if you had to do it by digital numeric means versus this geometric means, which algorithm to tell you if it's prime is more economical?
with a digital number, I use Eratosthenes prime. It's the simplest algorithm. I first test all the number before the square root of something. By brute force with 33 number, and then I solve it.
And with the geometric, the simplex?
If I can see in n dimension, I can see how many dimensions.
Okay. But there's computational ways, mathematical ways to see. He doesn't mean visual. He means if you can mathematically. So it's harder.
I can see this for the 3, and then like the 3 is prime. And I can see for the neutral one that the 4 is not prime. But after that,
So not necessarily more, not more economical.
I see. But can you find a general formula, an analytical formula that predicts the number of primes in the system? Do you have a universal formula that can tell you immediately if you plug in a number and it's 1000, and you can spit out the formula? Or you can only calculate the coefficients?
I know that there is a universal formula which will give you only primes. But there is no formula to put the number, and it will say it's 500. It's with number means
Terrence Howard, the United States, is leading the New Zealand, and those guys are using more and more powerful supercomputers. It's system of digital images. It's the they are deeply into predicting analysis by number theory, where you have more things to analyze. As I tried to demonstrate, you just have more non-arbitrary things to analyze and find ratios on this. I'm not saying it solves it for sure. I'm saying if we've spent hundreds of millions of dollars around the world in 150 years of modern times, and we're using digital number theory now with supercomputers to kind of deal with statistics, how about not statistics? How about go back to the question of why is there 23? This is a geometric object. It's a thing. It's a prime 100 simplex looking at 99 dimensions. Well, why is that? Why does it have 23 prime simplexes? Why is the distribution the way it is? So it's not just the count of 23, it's the distribution, the spacing. And why is that there? And you can simplify that the way that I showed you with the wings, and you can study it. And I believe these two series, primes really thin out. So it should surprise you that the circle radii actually increases in density. Because if you really understand how rapidly prime numbers thin, right, you should say, hey,